Right, welcome to the second half of this section, horizontal shifts. Horizontal shifts are not as nice as vertical shifts. We do have to remember something unique about them, okay? But they are the same three transformations. You can shift up and down, you can also reflect, and you can also scale. And once again, we see that the shifts and the reflections will be rigid, meaning our shape will not change. And the scaling will be the non-rigid. So whether you're talking x-axis or y-axis, inputs or outputs, you are looking at rigid and non-rigid, with rigid would be shifts and reflections, non-rigid would be scaling. All right, 10 on down. We have almost the exact same three problems as before, but this time they have been applied to the x. They're inside the function. And that's actually going to be a little tricky. So everything we do up to this point is opposite. Cool. Let's say, what on earth do you mean by that, Miss K? Let's just take a look at it as we do them. So we see these exact same function as before. We're going to probably need the exact same graph. So 1, 2, I'm going to make these small. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, it's not perfect, but it's good enough. Okay. Now, in the first one for vertical, we had y equals f of x plus 2. The plus 2 was on the outside. What did that do? That moved it up and down. We see a similar situation here, which means we're going to have a similar transformation. This is going to be a shift, but it's going to be left and right. Here's the thing, though. We need to keep our y value the same. Since y is an output, we don't want that to change. And so we have to kind of reverse engineer this function. Don't worry, it's not as complicated as it sounds. But we're going back to the original function, which means instead of going right, as it implies, we're actually going to be going left. So all of our points here are going to be left 2, because we're going backwards to our original function. Okay, if you want more information on that, please, by all means, reach out to your teacher and have them explain that to you. But for this video, we're just going to know that it's opposite for horizontal functions, okay? Horizontal transformations, pardon. So that means our points 0, 1, 2, 3, 4, 3, and 5, 5 are all going to move left 2. 0, 1 becomes negative 2, 1. 2, 3 becomes 2, 1. No, I'm sorry. Becomes 0, 3. Don't change the y, change the x. 4, 3 is going to become 2, 3. And then 5 is going to become 3, 5. Oops. There we are. And we see it's the same function, right? But it's over, so that rigid motion. Lovely. Again, similar, we have y equals f of negative x. In the first video for vertical transformation, the negative was on the outside. It was affecting the y's. This time it's affecting the x. Again, we're gonna see some things.
Mackenzie Hire, if
Sorry
you're in the
about that.
building, please call the main office. Mackenzie Hire, call 65604.
Yes, I'm videoing this at school. Anyway, so what's going to happen here is not a reflection over the x-axis, but you guessed it, a reflection over the y-axis. So this one's not as bad. Reversing, so when you multiply by a -1 and divide by a -1, the same thing happens. So we're still doing the opposite. Instead of multiplying everything by -1, you're dividing. But at the same time, I mean, what happens? It's the same thing. So what we get is 0. This is going to stay 0. I'll use a different color for this one. Let's name them as well. Let's name this one, we already used H, F, G, and H. Let's use J. We used K. Let's use M and N. Okay, so this original one was J of X. Now, M of X is going to be 0, 1. That doesn't change when you divide it by -1. Out 2 is going to change, divide that by negative. You get -2, 3. -2, 3. Okay. And then -4, 3, and -5, 5. And we see a reflection over the x-axis. That beautiful blue one has flipped over to be the red one. This is M of X. Oops. All right. The last one, we have, again, a similar situation. The last one, we have a stretch of 2, but this stretch is not applied to the y's, it's applied to the x's. And so instead of multiplying, we're going to divide. It's always the opposite if it's inside, always the opposite. So we're going to take each one of these x's and divide it by 2. use purple. 0 divided by 2, luckily, again, just 0. 2 divided by 2 would be 1. So this is now 1, 3. Okay. And then 4 divided by 2 is 2, 3. This one's a little awkward. 5 divided by 2 is 2.5. So we would be there-ish. Just want to make sure I get in there. Okay. And notice it has been squished. So when we divided it, it's now half as big. And we get a squishy function instead of a stretched out function. So again, it's opposite. All right. Let's use that now. So these are all the things that you could do with x. All of the ways you can manipulate this function. Again, we see the shift and the reflection totally rigid. They stay the same size, but that scaling, definitely non-rigid, it squished it down. If I had been multiplying by a half, we would see a very elongated x. It would be stretched out. So again, opposite. Let's use that now for example 4. Very, very similar to the first one with the verticals. Example 4, graph f of x is equal to the square root of x and plot at least 3 points. All right, we can do that again. Use transformations to graph g of x is equal to the square root of x plus 1. That is not quite the same thing, as what we had before. State the domain and range of g. Is this a rigid or non-rigid transformation? Okay, so let's go ahead and plot f of x here. Again, we'll make our little table. This one I think I'm just going to bank on the actual 3 points we come up with, okay? So 1, 2, 3, 4, 5, 6, 7, 8. Square root of x, if you remember from the last one, we have 0, 0, 1, 1, and 4, 2. This is our f of x function. Now let's look at this g of x function. What's going to happen? We're going to have dividing everything by a half, and then we're going to go left 1. Okay, so everything divides by a half, and then we're going to go left 1. Let's look at our points here. Got 0, 1, and 4 being 0, 1, and 2. Now remember, we're going to do these moves on the x's. So what's 1/2 of each of these x's, these original guys here? That's going to be 0, 1/2, and 2. Okay, cool. That's going to squish it down a little bit, right? Now we're going to add 1 to each of those, which means we're going to go left 1. I'm just going to plot that part. Easier than writing it down. Ooh, that was awkward. Sorry. Okay, so all of my y values will move. Oh no, my x values will move. Actually, well, it's not that hard. We'll just go left 1. So that goes, this thing here would be left 1 would be -1. This would be 1/2 would become -1/2. And this would be, left 1 would be 1. And so my points now are -1, 0, -1/2, 1, and 1, 2. Okay, let's go look at that. So -1, 0, -1/2, 1, and 1, 2. We see a much squishier function, and it has been moved left. Okay, whether you want to do the table or the graph or both, that's up to you. Eventually you have to graph it because they asked you to. But if the table part isn't the way you want to do that, you just want to move all those points left, that's fine too. Honestly, some people are visual, some people are algebra, some people need to see the numbers, some people are okay with just the points. However that is, whatever your drive on that is, go with it. All right, state the domain and range of g of x. I think that might be easier if we look at the function itself. So what is an issue with the square root? Well, the square root here cannot be negative. Never can a square root be negative. What's the first value that's going to do that? I'll give you the hint. It's right there. -1 to infinity. What about the range? The range is not going to come out with any negative numbers here, so 0 to infinity is our domain and range. And this was definitely a non-rigid transformation. You're like, wait, Miss K, I thought it had a rigid one in there, so technically it's both, right? If you ever move it once non-rigid, kind of just blows it for everything. Okay, if you don't maintain that rigidity at any point, it's called a non-rigid transformation. So even this combination, because technically moving things left to the one, non-rigid, right? But since we squished it comparing just the two functions, it's a non-rigid transformation. All right. Now in the next video, we're going to look at a combination of functions. I will see you there.